So in the previous section, we had discussed about the gear tooth profiles on a SPUR gear and gear nomenclature. And this section we are going to discuss about the force analysis of a SPUR gear, right? So we can see that here that this is the pinion or the driver gear, and this is the gear or driven gear, and this is the pitch point where the two pitch circle meet. And here the force acting at an angle alpha with the common tangent, and this force F can be resolved into two components, Ft along the tangential component or Ft along the tangential direction is known as a tangential component, and this is the radial component. So this radial component tries to separate the two gears, right? Okay, so by log gearing, resultant force F always act to the pressure line. Okay, and since the pressure line is inclined at an angle alpha, the resultant force at pitch point can be resolved into two components, the tangential component Ft and radial component Fr, right? So we can find out how to calculate this tangential and radial component. The tangential component can be calculated by using this equation. This equation equal to Ft is equal to mt, where mt is the torque that we transmitted, torque by d by 2. D by 2 is the base circle diameter divided by 2, and force equal to torque by perpendicular distance, or torque is equal to force into perpendicular distance. We know that. So Ft is equal to 2mt or torque divided by d, where mt is the torque transmitted and d is the pitch diameter. The torque transmitted can be calculated by using this equation, where P is the power, 2 pi nt by 6t is the power. Okay, so mt is equal to 6gp by 2 pi n. We can write that. Then radial component of force Fr. From this triangle, right angle triangle, we can see that radial force Fr is equal to Ft into tan alpha, and the resultant force F is equal to root of Ft square plus Fr square. Substituting this in this equation, we get F is equal to Ft by cos alpha. So the power transmitted P can be written as P is equal to Ft into V, where V is the pitch line velocity. That is the velocity at this pitch circle, the linear velocity at this pitch point, and that is equal to pi dn by 60, where n is in RPM, rotation of this gear. The strength of a gear teeth is being calculated by using beam strength equation, and that equation is known as Lewis equation. This has been formulated by Wilfred Lewis in 1892, and the Lewis equation is based on some assumptions that the effect of the radial component, that here Fr, which indicates compressive stress on the teeth, is neglected, and the second assumption is that the tangential component Ft is uniformly distributed all over the face. That Ft is uniformly distributed all over the face, here like that. And the stress concentration effect is neglected, and at a particular time only one teeth is in contact with another teeth, right? So these are the four assumptions for formulating Lewis equation. So consider here that we are changing the profile of the gear teeth in parabolic shape. This is because a beam is of uniform strength, because parabolic shape provides a beam is of uniform strength, and the height of that parabola is h, and the Ft is acting on the tip of the parabola. So here we know that the bending moment mb can be calculated by using Ft multiplied by h, right? And the moment of inertia of this cross section about this axis, that is equal to btq by 12, and y1 is the distance from this neutral axis, right? So maximum y1 is t by 2. And also from the bending equation we know that m by I equal to sigma by y, or sigma b, or bending stress equal to mb into y by I, or that is equal to mb by I into y1 is equal to mb by zm, right? So consider this term as zm. Next, substitute the value of moment of inertia I and y1 in this equation. We will get sigma b, where sigma b is the bending stress. Consider that it is a permissible bending stress, or the permissible stress for the material, and that is in Newton per millimeter square. Then by applying I and y1, we will get 6 ft into h by bt square, right? Or ft is equal to bt square into sigma b by 6 into h. So multiplying the numerator and denominator by pc, that is circular pitch, we will get pc into b into sigma b multiplied by t square by 6h pc. So this term is in bracket. So this bracketed quantity, that is known as Lewis form factor y, and thus Lewis form factor y depends upon the forms of the teeth, because it depends upon the thickness of the teeth and height, right? So form factor depends upon the forms of the teeth, right? Then the equation can be written as pc into b into sigma b into y. Apply this y here. So this is the equation for tangential tooth load. And when the stress reaches the permissible magnitude, the bending stress corresponding to that force, that Ft, when this stress reaches the permissible value corresponding that Ft, is known as beam strength, or it is represented as Fs. So F is equal to sigma b into Pc into B into Y, and that is equal to sigma b into B into Y into pi m. Apply Pc as pi into m. We know that Pc equal to, or pitch, circular pitch is equal to pi into m, and Fs is the beam strength of the gear, that is in Newton or kilogram force, and sigma b is the permissible bending stress, and that is in Newton per millimeter square or kilogram forces per centimeter square. So that equation is on PSC data book page number 8.50. Please note it down. Okay. The Lewis form factor for different tooth profiles is on PSC page number 8.50. So y is equal to this value for 14.5 full depth involute gear, and y is equal to 0.155 as a value for 20 degree involute, and y is equal to this one for 20 involute step teeth. Okay, step teeth means the depth is less than the full depth, right? So that is known as stub teeth gear. So these are the two types of gear teeth profile: full depth and step teeth. And we know that sigma b is equal to Ft by B into Y into pi m, right? So consider the effect of impact created by velocity of the gear during the engagement. While considering that one, we will get a sigma b is equal to Ft by Cv into B into Y into pi m. That value Cv, that is known as velocity factor, right? So therefore we can write a sigma b into Cv is equal to Ft by B into Y into pi m. This is another equation while considering the effect of impact created by velocity during the engagement. Next one, dynamic load calculations. When a gear rotates at a slower speeds, the tangential load Ft itself can be used for design, because there is no other factors to be considered. But when the gear drive start rotating at a higher speed, it is decided to calculate a dynamic load for the design, and the dynamic load induced due to the following factors. First one, inaccuracies in the tooth profile. The tooth inaccuracies that occurs during the tooth profile, and errors in tooth spacing. and misalignment between the bearings, and elasticity of parts, and last one, inertia of rotating masses. So when these conditions occurs because of the higher speed of the gears, and when this condition occurs, we have to calculate the dynamic loads, and there are two methods of finding the dynamic load. First one is the approximate estimation by velocity factor in the preliminary stage of gear design, and the second one, the Buckingham's equation, and that is used in the final stages. So the dynamic load by velocity factor, this equation is mainly used to find out the dynamic load by velocity factor, and is generally used in the preliminary stages of the gear design, where Ft, the dynamic load, is equal to Ft into Cv, and the velocity factor Cv depends on the pitch line velocity and the quality of the gear. There are so many equations for finding out the velocity factor. The first one is Cv is equal to 3 plus Vm by 3, and this equation is used when Vm, or the pitch line velocity, is less than 10 meters per second, and is used for ordinary and commercially cut gears. And another second one is Cv is equal to 6 plus Vm by 6. This one is used when the velocity Vm is in between 5 and 20 meters per second, right? So this is for accurately hopped and generated gears. The velocity factor, this equation is used, and Cv is equal to 5.5 Vm all raised to 1 by 2 divided by 5.5, and this is used for precise gears with shaving, grinding, and lapping, and the velocity, or the pitch line velocity, is greater than 20 meter, actually 20 meter per second, right? And the fourth one, Cv is equal to 1 plus Vm by 1 plus 0.25 Vm, and this is for non-metallic gears. These equations are on PSG data book, page number 8.51. So next one, the dynamic load calculated by using Buckingham's equation. This one is very important, and by this equation, that a dynamic load Ft is equal to Ft plus Fi, where Fi is the incremental load due to dynamic action, and Ft is the tangential tooth load. So there is an incremental load acting in addition to that tangential tooth load, and that value can be calculated by using this equation: 0.164 Vm into Cb plus Ft divided by 0.164 Vm plus 1.485 root Cb plus Ft, right? So here these are some values, and the Cb, Vm and Ft, Cb, Vm are calculated by using some equations, right? And C is the dynamic factor, and that is in kilogram forces per centimeter square, and that depends upon the machining error, how much error is happening on that machining. Okay, so, and next one, E is the measured error between gear in centimeter. Okay, and B is the face width of the gear tooth, and Ft is a tangential tooth load, and it's a kilogram force, and Vm is the pitch line velocity. So by using this equation, we can calculate the dynamic load. So the constant or this dynamic factor is calculated using this equation. Here C is equal to E by K into 1 by E1 plus 1 by E2, where E1 and E2 are the modulus of velocity of pinion and gear respectively, and that is in kilogram force per centimeter square, and K is a constant depending upon the form of the teeth. So by this equation we can calculate this C right here. Due to the contact between the two teeth or mating gear, there will be contact stresses developed between the two teeth. So this causes wear on the tooth surfaces. So we have to find out, it is important to find out the wear tooth load before designing a gear teeth. And that equation can be calculated by using that wear tooth load can be calculated by using this equation, that Fw is equal to d1 into b into q into k, where Fw is the wear load, that is in kilogram force, and d1 is the pitch circle diameter of the pinion, that is in centimeter, and b is the face width of the pinion in centimeter. And that those equations are in PSG data book page number 8.51, where q and k can be calculated by using these equations, where q is the ratio factor, and that depends upon the velocity ratio. The velocity ratio I is equal to z2 by z1, right? And the q, the ratio factor, is equal to 2i by I plus or minus 1. This plus sign is used when the gears are external gears, and minus is used when the gears are internal gears. And that's equal to, this is equal to 2 into z2 by z2 plus or minus z1, right? And this equation also in PSC data book page number 8.51, right? So here I is the velocity ratio and K is the load stress factor, also known as the material combination factor, that is in kilogram force per centimeter square. So K can be calculated by using this equation. This is known as load stress factor, that is equal to sigma square sine alpha into 1 by E1 plus 1 by E2, where E1 and E2 are the modulus of velocity of pinion and gear respectively, and divided by 1.4. Okay, so sigma C is the compressive stress on the gear tooth, and by that equation we can calculate the wear strength of the gear tooth. So these are the major equations that are used for designing a SPUR gear. In the next class we can discuss some problems in this topic.